Alright, for this example, if we're going to find approximations for this definite integral using the midpoint rule and then using the trapezoidal rule, and we're also going to take a look at the absolute error. In other words, we're going to take a look at how close are our approximations to the actual value of 4. The best way to do this, I think, is to organize the information in a table. So we're going to start with the first column being values of n, and the second column will be the values that we get using the midpoint rule for the particular value of n. And then we'll look at the absolute error for the midpoint rule. So, using the calculator to do this work, and get this where you can see it. Well, that wasn't the answer. Move, darn ya. Okay, using the calculator, there we go. You have to have the function in y1. And then if I'm going to use the Riemann program, select that from your list from programs, enter the lower limit, enter the upper limit, give the number of subintervals, and if we want midpoint Riemann sums, which is what we want for the midpoint rule, enter 50%. So the value that the calculator gives me here is 3. Now, while you have that value in the calculator, take the actual value for the definite integral 4 and subtract your last answer. Now, 4 minus 3, of course, we know is 1. But when you get decimal numbers that get rather a little lengthy, it is much easier just to calculate the error while you've got that exact decimal number in the calculator rather than try to type it in again later. So pause the video at this point and fill in the rest of the column for the midpoint rule and the rest of the column for the absolute error. Check your answers. And then we want to move on and get trapezoidal rule approximations. So the next column, we'll use the trapezoidal rule in the trap rule program in the calculator, and then we'll take a look at the absolute error for the trapezoidal rule. Again, as long as your function is in y1, you're ready to go. Select trap rule out of your list of programs. Enter the lower limit, the upper limit, and the number of subintervals. Okay, we get a trapezoidal approximation of 6. So the absolute error in that particular case is 2. Now, you're not always going to get whole numbers. So, like the next one that we do with n equal 8, (4.5). Certainly the difference there is something that's easy enough to do, but leave that 4.5 value in your calculator. Take 4 and subtract your answer from that to get the amount of error. That's going to become more and more important as you fill in the later boxes. So pause the video again and fill in the rest of those 2 columns. Alright, check your work. Now, one thing that I kind of think is interesting about this example is that notice that the approximations we got with the midpoint rule are all a little bit less than the actual value of 4, and our trapezoidal rule approximations are all a little bit more than the actual value of 4. It's also interesting to note that the amount of error is smaller for the midpoint approximations, which kind of surprises me. I typically would expect trapezoidal approximation to be a closer estimate than an approximation using rectangles. In our next example, where we're working with a definite integral from 1 to e of a natural log of x, we're going to do basically the same thing, except we're going to compare values that are approximations we get with the trapezoidal rule to approximations we get using Simpson's rule. So we're organizing our information the same way we did in the last problem, where our first column is the values of n. In the second column, let me get my pens ready. In the second column, we're going to put in the trapezoidal approximations. Third column then will be the absolute error. And then we'll have the approximations we get from Simpson's rule and the absolute error there. Trapezoidal rule, I know you know how to do. For Simpson's rule, let me pull up my calculator and get it where you can see it. Not there. Okay. Your function has to be in y1. So we are integrating the natural log of x. So I'm going to put that in y1. Second quit. There we go. Now I'm going to run the Simpson program, which is option 7 in my calculator. The lower limit was 1. The upper limit was the number e. You can either do e to the first power using the second function of the natural log key, or you can use the second function of your division key, which is just the number e. So that's our upper limit. We're going to start with 4 subintervals, and the calculator thinks for a bit, and the value we get there. This is one of those times where you're going to have more decimal places than you have room to write on your paper, possibly. Write down as much as you possibly can. Let me get that always on top. So 0.9997079, and I'm out of room. Remember, the more decimal places that you write down, the more accurate your answer, and the happier your teacher is. For absolute error, the exact value of this integral was 1. So we're going to take 1 and subtract our last answer. So we haven't rounded anything off. And then the error here, because it is so small, is given to you in scientific notation. You're welcome to write it in scientific notation when you fill in your table, but I would recommend that you actually write it in standard notation. So you're able to really focus in on how small that number is. So if we're multiplying by 10 to the negative 4th power, that's going to be the decimal point and 3 zeros before the first digit. Now at this point I want you to pause the video and fill in all the slots for the trapezoidal rule and all the remaining slots for Simpson's rule. Alright, check your answers. You notice that in both using the trapezoidal rule and in using Simpson's rule here, we've got approximations that are very, very close to the actual value of 1. And I think it's noteworthy to sort of pay attention to how incredibly close to 1 we get with Simpson's rule, even with just 4 subintervals, which is really not going to be that great an approximation. The other thing to think about is we have a relatively short interval from 1 to e. It's not a very it's not a very big interval of real numbers, and if dividing that up into 4 sections, your subintervals are pretty small. Dividing it up into 32 subintervals, you've got really, really tiny subintervals, and an approximation that if you were rounding that off to 3 decimal places, that would be 1.